Hey everyone, so this is your next week of HPL, and today we're going to be covering on sound. As I've already given you quite a short introduction, and if you remember that horrendous period where everything seemed to go wrong, I hope that you still have at least some idea what we're going to cover in this chapter. So yeah, without further ado, let's carry on. Now, you should have already watched the other video that I mentioned on Google Classroom, the one where we see the slow-mo guys and they are actually playing the tuning fork. And from that video, you can see that the tuning fork has to be constantly vibrating in order for it to produce a sound. Okay, and that also ties into what we actually covered in class, where sound is caused by vibration. Now, if you actually look at the bottom right hand corner, this diagram over here as well, what you can see is this animation of particles so-called being pushed to and fro by this grayish whatever that is there. So imagine that that is the tuning fork and it's pushing the particles to and fro. And if you take at a first glance, right, it seems that the particles are moving from left to right. But if you pay attention very closely to the red particle right here or the red particle right here, you can see that it's actually only oscillating left and right. Okay, so this proves that sound itself is really a longitudinal wave in which the vibration is parallel. Okay, so the keyword being parallel to the direction of the wave itself. So this is how sound transfers its energy. It is through these vibrations, and you can see the compressions and rarefactions, where you can see like these layers of air actually moving. Those are the compressions in the longitudinal wave. Okay, so hope that gives you a clearer picture. Let's move on to the next slide. So if you may recall, right, now this is just a very static diagram of how sound is produced. I mentioned to you guys that at O level, you really need to be able to describe how sound is being produced. We have already done this in class, but let me just quickly refresh your memory. So if you imagine that there are these layers of air that are stationary at first, okay, and so what happens is when sound waves are produced, what happens is that the vibrating object will push and pull on the air adjacent to it. Now, this is very important. It's either the immediate layer or adjacent to the tuning fork in this case. Okay, so when the prongs actually move outwards, what happens is it will compress the air at this point here, and this will actually cause a change in the air pressure. Okay, so when there's compression, you can imagine that there's higher pressure acting on the air. So as well, we can see here when the prongs move outwards, these layers of air are pushed close together, and hence there's compression of the air particles. So at this point, when the prongs actually move inwards, what happens is that we have layers of air actually being pushed apart. So what we call this area here, it is the decompression or the rarefaction of these air particles. Okay, so you can imagine that these prongs keep moving in and out. And what happens is that we have this whole series of compressions and rarefactions. And the direction of the sound wave in this case is to the right. Okay, so we have then sound propagated in the form of longitudinal waves. So I want you to study the diagram a little bit carefully as well. You can see that they even tell you that the compression is of high pressure, rarefactions are at low pressure, right? You can see the compression. This is where all these layers of air are so-called squeezed together. Rarefactions are when the layers of air are more spread out. Okay, and more importantly, right, actually, when you see these layers of air, you can see that a wavelength is either from the compression to another compression. You can also define the wavelength as the center of the rarefaction to another center of rarefaction. So in case you're asked to determine how to get the wavelength of a sound wave, is a center of compression to another center of compression, or center of rarefaction to another center of rarefaction. So what we are going to show you here is that if you remember, I tried to draw the pressure and position graph of a sound wave, right? So if you are asked to sketch the pressure and position graph, you need to know that basically at the center of compression, that's where the pressure is at its highest. At the center of rarefaction, the pressure is at its lowest, and this carries on so on and so forth as what I am drawing here. Okay, so the quick question here is, and I think you really can answer this, why do we say that if there's no air, there will be no sound? Okay, so we already kind of covered this in class, so in case you just need to think about it again and refresh your memory on why sound actually requires a medium. Okay, so if you also recall from the introduction lesson, right, we mentioned a little bit about echoes and how sound waves can bounce off a wall and they return to us. So some applications in the animal world, as I already mentioned. Now, there are certain animals that actually make use of this echolocation in order to detect maybe their prey, because maybe they don't actually see very well, especially in the deep murky waters, right? But what they can use is the application of echoes in order for them to detect their food. Okay, so for example, they will emit a sound wave, and this sound wave, when it bounces off their prey, like in this case here, this poor fish here is the prey, right? They can actually detect how far the prey is from them and hunt them down. Okay, and I know we talked a little bit about the bats, and yes, people are all talking about bats these days due to COVID-19. So bats also make use of echolocation. They are able to sense their prey or detect distances, estimate the distance from the prey to the bat or from another wall to the bat itself, and that's how they actually fly around and find the things that they need in order for them to survive. So these are just some other pictures of other applications that make use of echolocation. And uh, what you are actually seeing here is a submarine that makes use of the same idea. Okay, so in a submarine, right, it's not like you're going to drive a submarine or pilot a submarine using a window and then, okay, you just take a look around. That would be kind of ridiculous. Okay, if you actually seen the inside of a submarine, they don't exactly have windows in that sense to guide them. So what they actually do is also to make use of echolocation in order to pilot the submarine and make use of these radars or instruments in order for them to get around. Okay, so this is how mankind actually is inspired by nature sometimes in order to build certain applications or to create technology to help us in our real world. All right, so this was on page 2 of your notes, and what I just quickly want to highlight is that when you calculate questions or when you do questions on sound waves, right, you need to make sure you know how the sound is actually traveling. That's why we say that you must be able to trace the path of the sound wave to determine the total distance that the sound wave travels, okay? Uh, Please pay attention to this. Usually, the path is simplified and as straight lines, and we don't want to take into account any of the angles. Like for example, now if let's say you see in this diagram, right, there's a clap, the sound travels, and then it reflects back, right? Okay. Now we will usually ignore this whole portion in that sense. We just take it as if it really, okay, it went to and it went back in that sense. Okay, it's easier for us to actually understand it that way. Otherwise, we have to take into account angles, we have to take into account, you probably have to use trigonometry to go and solve certain things. Okay, so it is really not necessary for you to take into account the angles. So just a big note here, angles, in this case, you don't need to take them into account. Okay, and speed of sound is constant in one medium. So there are usually only two formulas you want to take note. Distance equals speed times time, or sometimes we'll make use of V equal F lambda. Okay, of course, if you recall, right, sometimes we are giving you the distance in one particular direction. So when do you use the distance times 2? Is when you know that there's an echo involved, then only then you will take the distance multiplied by 2. Okay, now one thing that all of you should always try to take note, and this also applies to many of your wave questions or even light questions, right? Frequency usually is constant, okay, depending on the vibration of the source. All right, so the medium, right, does not determine the frequency. Okay, so just pay attention to this. So most of the time, if let's say we know that that particular source already has a particular frequency, there's no need to worry whether that frequency changes as it travels through different mediums. Okay, of course, frequency of sound can change depending on pitch, but that's for another later lesson, and we'll explore that later as we go along. Okay, stop right now. Before you actually carry on with this video, I want you to take a pause here because I want you to actually attempt the questions on how to calculate the speed of sound or the distance involved. And this will be page 2, question 4. This actually falls over to page 3 as well. So I want you to just pause the video here and attempt the entirety of question 4. And please be only sure to carry on after you have attempted it. Please don't cheat and just look at the answers or the working in the video. Okay, so we'll pause it right here first. Right, so this first question or the first part of the question requires you to actually calculate the wavelengths of the ultrasonic waves in air and in water. Okay, so you're given the frequency, you're given the speed respectively in air and in water. Okay, so I hope you can recall your equation V equal F lambda, and hence your first answer lambda will give you about 2.8 meters. This is for the wavelength in air, and for in water, also applying V equal F lambda, you will get about 0.013 meters. Okay, now for part B, so this is one way and one application in which ships can actually estimate the depth of the sea. Now you would of course not say, okay, I'm going to measure the depth of a sea with a measuring tape, right? Where on earth are you going to find a measuring tape that long? So this is another application of echo. Okay, so let's take a quick look. So if you imagine a ship emits ultrasonic sound wave and it hits the bottom of the seabed, actually sorry, the bottom of the sea hits the seabed, and this sound wave is reflected back to the ship where a sensor will pick it up, and from there we can actually determine how long it took for the sound wave to travel to the bottom and back to the ship. Okay, remember I can say that we assume the path travel is vertical. I know on the diagram we drew it to be slightly slanted. We take it to be a very, very small angle, and hence it is actually kind of negligible. Okay, so let's take a quick look at the working. Now the distance, as we know, is equal speed times time. Now this sound wave travels to and fro, hence you need to talk about 2 times the depth of the sea, which F therefore equals to the speed of 1500, and the time taken was 15 seconds. So hence you should get a depth of approximately 11,000 meters. We take it to the least SF, which is 2SF in this case. Right, so now let's take a look at the other question, where the ship on the sea is hit by a bomb, and a man swimming hears 2 sounds of explosion which are separated by 1 second. Okay, I know the part A in this slide doesn't exist on your notes, but maybe you want to think about this. Why are there 2 sounds of explosion? Okay, you may want to pause here a while before you look at the answer. So there are actually 2 sounds of explosion because think about it. This is the bomb. The man is swimming over there. Now, there are 2 mediums involved. One is air, which is a gas. One is the sea, which is a liquid. So we actually covered this in the introduction lesson. So the bomb travels both in air and in the sea. Okay, and why do you think we drew the diagram such that the sound wave actually in the sea reaches us first? So what you actually need to recall is that sound travels faster in liquids as compared to gases. So the 2 sounds actually arrived at the man at a different time. So we also know that the speed of sound differs in different density. Since water is denser than air, the first sound he hears is actually the sound traveling in water, and the second sound is the sound traveling in air. Okay, so how do we find the distance between the man and the ship? This one is a little bit trickier. You cannot just directly apply the formula that you know, but what we do know for sure is that the distance from the man and the ship must be a constant. Yeah. Okay, that means the distance in the air, that means how long the sound travels, must be the same distance in water. So we can form an equation already. The speed of sound in air multiplied by the time taken plus 1 second. So if you remember, this thing was separated by 1 second, right? Must equal to the speed in the water multiplied by the time taken. Okay, so all you have to do is substitute in the values and you will get 340 multiplied by this t plus 1 will give us 1450 t. Sorry about this. This should be small letter t. So t equals to 0.306 seconds. So once you can find the value of t, you can easily find the distance between the man and the ship, which is, we can make use of this distance in water. So distance must equal to 1450 multiplied by that 0.306, and hence we end up with about 440 meters. Also, least SF, so 2SF please. Okay, so that's for today. I will put up another lesson for tomorrow where you will carry on and we'll learn other concepts about sound. Please do take the time to refresh or review the video again if you need. And tomorrow will be a slightly more difficult concept, and we're going to look at how the various graphs uh, regarding waves can be applied to sound itself. Okay, until then, take care and have a great day.